Okay, we want to continue with our examples on the node voltage method. And what I want to do now is let's look at an example when we add a dependent source. So we put a dependent current source here. So the only difference between this and the last example is that there's a dependent source here, and of course when we have a dependent source, as you know, we have to have a current or voltage that controls that dependent source. So we'll call this I delta, and then this current source will be 3 I delta. So I delta is the controlling variable. It's what controls the output of that dependent current source. So this is a current controlled dependent current source. And so now let's solve the system using the node voltage method. So what you need to do initially, my opinion, is you don't do anything with the dependent source until you kind of get to the very end of the setup. So we're going to proceed just like we've been proceeding. Going to identify the nodes, this one being this whole upper branch, and then we've got one whole big node at the bottom. Let's look at our sources. We do have a voltage source. If we connect the reference or ground node to the negative terminal of the voltage source, that would mean our reference would be down here at the bottom again, and then we can label our node voltages as V1, V2, and V3. And so for now, we're going to treat the dependent source like it's any other current source, and you'll find when we get to the end of the setup that we're going to need one more equation, which we'll add at the end. So the first thing we see is that we have a source equation that defines node V1. So we can call that a source equation. That's what I call it. I don't know that that's necessarily a term that's used everywhere, but that's what I call it. That's V1 is 4 volts, so that's one of your equations. Then we'll need a node equation at V2. So we'll have V2 minus V1, which is 4. So we can either substitute that in directly or put V1, since you've got V1 defined here. If you don't have V1 defined with a separate equation, then obviously you would have to put your 4 volts in directly. So we have V2 minus 4 over 1. We have 1 amp entering the node, and we have V2 minus V3 over 2. And please note that I'm completely ignoring for the time being that dependent source, or that control variable I delta. Okay, and then at V3, make sure we show it, I'll have V3 minus V2 over 2 plus V3 minus 0, which I won't put in, over 3, and then a minus 3 I delta. So note that I just put that dependent current source in exactly the same way I entered the independent current source. The only difference is it's got this controlling variable. So now I need to define what is I delta, and I refer to this as the dependent source equation. Once again, that's just my terminology, not always seen in books, but that's what it is. It's going to be the equation that determines the dependent source variable. So I guess you could call that the dependent source variable equation. So what we want is we want to know what is I delta. So what is I delta? Well, it's the current through the 2 ohm resistor. So it would be the voltage difference across the 2 ohm resistor divided by the value of the resistance. Okay, so why did I pick V2 minus V3 instead of V3 minus V2? because the current is always defined as flowing from the more positive to the more negative terminal of the resistor. And so from the definition of the circuit here, I've kind of made an implied assumption that I've got a voltage drop here. So I'll write it as V2 minus V3. Now it may turn out that after this is solved, every single variable turns out negative because, you know, of the way the solution comes out, but that's okay. Alright, so this is actually a very easy problem. Once you substitute in for V1, you have 3 equations and 3 unknowns, and once again the issue just becomes the solution of simultaneous equations. So as I said earlier, we'll leave that for another lecture. Right now I'm really trying to point out how you write equations to solve circuits using the node voltage method. So once you solve things, then you of course will know that you've got a voltage drop across this 1 ohm resistor. You'll know that because it'll be the difference between V1 and V2. You'll know that the voltage across the 1 amp source is going to be V2. The voltage across the 3 ohm resistor and across the 3 I delta dependent source is going to be V3. The current through the 2 ohm resistor is I delta. The current through the 4 volt source, 2 options. Because it's in series with the 1 ohm resistor, the easiest thing to do would be to calculate the current through the 1 ohm resistor by taking the voltage difference divided by the resistance. And then that's going to be the same current that goes through the 4 volt source because they're in series. So that by far is the easiest thing to do. So once again, the node voltages allow you to solve for any variables in the circuit. Okay, so the next thing that I want to do is I want to look at a circuit where we have 2 voltage sources that are not connected to the same node. Actually, first let me look at one. I don't know why this thing keeps skipping around. First, let me look at one where you have 2 voltage sources that do share a common node. I seem to like 4 volts today. So we'll do this. So let's look at a circuit like this using the node voltage method. So the first thing, once again, that we do is we come in and we identify the nodes. And this is why I don't like that whole non-essential node thing, is I think for a problem like this, just marking all the nodes is kind of a big deal. And now notice that the negative terminal of both of these voltage sources shares a common node, and so we'll put the reference there. And then we'll label these others V1, V2, V3, and V4. Oops, sorry. Let me put a resistor there. I meant to do that. And we'll give these resistors some values. Yeah, I meant to put a resistor there. Okay, so obviously you could combine the 2 and the 4 in series, but let's just kind of leave it like it's drawn so that I can illustrate the point that I want to illustrate. So first of all, because the first thing is, if you have 2 voltage sources, look and see if they share a common node, and if they do, then make that common node the reference, because if you do, then V1 is 4 and V3 is 2. And you've already solved half of your nodes. So now you just need a node equation at V2. So you have V2 minus 4 over 1, V2 minus V3, which is 2 over 3, and V2 minus V4 over 2. And then at node V4, and once again, you could combine the 2 and the 4 in series and simplify the circuit a little bit if you wanted to and eliminate a node, but we're not doing that at the moment. So at V4, we have V4 minus V2 over 2 plus V4 over 4 is equal to 0. So actually turns out to be a very simple problem. We're going to talk about mesh current in the next unit of things that we do, and a lot of people would look at this and say, oh, this is much easier to use mesh current, but it turns out using node voltage is an extremely easy method here. Now I want to do one thing at the risk of confusing the notes later. Let me see if I can copy and paste this. I don't seem to be able to do that. Just trying to copy and paste this drawing. It's not going to let me do it. So your notes are going to look a little bit odd. But let's make some comments so that if you do go back and review the PowerPoint, you understand. So the pink markings what we want to know is what is different if the polarity of one of the sources changes. We won't say changes, we'll say was different. So in other words, if in the original problem, say this 4-volt source, and we'll make this marking in pink, say this 4-volt source had been minus plus instead of plus minus, so that the positive terminal connects to the ground. So what actually would be the difference in that case? So in that case, the difference would be V3 would still be 2 volts, but V4 or V1, notice the difference between V1 and ground. In the pink case, ground is more positive, but it's 0. But the source is a 4-volt source. So in the case where the positive terminal is connected to the reference, then the voltage is negative, because you actually are dropping. If you look at the pink, if the case with the pink polarity, you're actually dropping as you go from ground to V1. So this is example of flipped polarity. That way, for those of you that don't want to watch the video a second time but want to look at the notes, you'll know what you're looking at. Okay, so pretty straightforward. Once again, no real big issues there. So now what I want to talk about is the case that tends to confuse students, but is actually not incredibly difficult, just confuses people. So let's look at a similar case. We'll throw a current source in there just for good measure. Let's put another current source in there. Okay, so different kind of circuit here. So the first thing before we really do anything, even identify the nodes, we kind of glance and look at the sources, because that's going to tell us a few things. And so what we see here is we have 2 different voltage sources, and they're not connected to a common node. So that's okay. That just means we have to take another approach. So we're going to continue with our method. We're going to identify every node. And we have 5 nodes in this case, so we'll do that, and we'll choose the reference. We'll choose it at the bottom. You want to just be sure you choose the reference at one of the voltage sources. So that's, you know, either the 4-volt or the 2-volt, either one. We could put the reference. The reference does not have to be at the bottom, but we'll do it this time this way, because that's kind of been what we've been doing. And now I'm going to label my unknown voltages. And this V3 is for both of these branches connect to node V3. So I have 3 unknown node voltages. and then I have a voltage source in there. So the first thing that's obvious is that V1 is equal to 4 volts. Okay, and the second thing that's obvious is that V3 minus V2 is equal to 2 volts. So these are my source equations. Okay, but that doesn't really tell me much. So the question then is, if I'm going to use the node voltage method, so we know for sure I don't need a node equation at node 1. And we know that there's a relationship between node 2 and node 3. So what do I do with this voltage source? So first of all, I'm going to show you the kind of awkward way to do this. So remember when we are writing node voltage equations, we're summing currents, but we're summing currents in terms of the node voltages. Well, in this particular case, the current through the 2 volt source is an unknown. And because there's no resistor there, we can't really use Ohm's law to get a definition for what it is. So we just have to pick a direction. And this is a random choice. I could pick it pointing to the left or to the right. Because I haven't solved the circuit yet, I have no idea which direction it actually flows. But I have to give it a name, and I have to give it a direction. And once I do that, I have to live with that because it's going to be a variable that I solve for. So I chose it to be from left to right, and it represents the current through the voltage source. So the first thing I'm going to do is I'm going to write the equation at node V2. Okay, that's going to give me V2 minus V1 over 1 minus 2 amps, and then I'm going to get this current leaving the node that I defined as I source. Okay, and similarly for node V3, I'm going to have I source now entering the node. Okay, and then I'm going to have V3 over 2, because it's V3 minus 0. And then I'm going to have minus 1 amp, because it's entering the node. Okay, so that's how I write my two separate node equations. And I had to define this source current. Now I want you to notice something. Let's add these two equations together. Okay, if I add my two equations, I'll get this term, this IS term here, and this IS term will cancel. And I'll have V2 minus V1 over 1 minus 2 plus V3 over 2 minus 1 equals 0. So I'll have a single equation that came about as a consequence of adding these two. Now there is a shorthand or abbreviated methodology to do that, and so we're going to use blue now. So we can skip the whole identify the current through the voltage source thing if we remember that really KCL equations are defined not for nodes but for closed surfaces. So what I'm going to do is I'm going to come in here and I'm going to put a closed surface that contains the entire voltage source that's not connected to the reference. And I'm going to refer to that as a supernode. And now I'm going to write a KCL equation or a node equation based on the branches that intersect that supernode. And there will be 1, 2, 3, 4. And you notice the voltage source and its current are completely contained within the supernode. So I'm going to have 4 branches that connect. On the left-hand side, they're connecting to the voltage V2. On the right-hand side, they're connecting to the voltage V3. So these 3 I'll write with respect to voltage V3, and these 2 connect to the other end. So first I will have V2 minus V1 over 1 and then I'll have 2 amps entering that surface, and then I will have V3 over 2, and then I will have 1 amp entering the surface, and that's it. And you notice that it is exactly the same as if I wrote 2 separate node equations with an undefined source current and added them together. So this is referred to as the supernode equation. And to answer the question that is burning in everyone's mind, yes, you will be required to know A, when it is appropriate to write a supernode equation, and B, how to actually write one. Okay? So that does it for all of the types of problems that you could encounter. We've looked at the supernode problem. We've looked at the situation where you have 2 sources connected to a common node, and what happens if you then flip, if one of the polarities of the source was different. We've looked at how to incorporate a dependent source into our equations, and we've looked at how to use just a simple node voltage method using a voltage source only. And we also then did an example for the solving of a system of linear equations. So I'm going to conclude here the lecture materials on examples of the node voltage method, and defer any additional examples or problem solving to any questions that anyone might have over the assigned homework. I will do an additional video on the use of Cramer's rule to solve simultaneous equations or systems of equations, because I think many people have never seen it before. And as I said, this has been my observation that this is one of the issues that people have with this particular material, is how to solve systems of equations. Even though that is an algebra 1/2 thing, it still seems to be a problem. So I want to address it before we get to having to do it with complex numbers. All right, so that concludes this lecture on the node voltage method.